If you miss anything or want to watch this again later, you should feel free to do that. I will send this out as soon as it is ready to go. So we're going to spend the next couple of hours just kind of practicing for our midterm. Let me also remind you that after the review, I also have office hours later tonight from 7 until 10. I know some of you might still be working on the homework. So you can certainly stop by and check that out. Ask me some questions in Zoom later on. I will have like a 1 hour break between the end of this and when I start my office hours. So that's kind of the plan. And then I'll be available for most of the evening as well. Yeah, and then I'll post the solutions to this last homework that you're working on right now. I'll get those posted later tonight, and then everything will be up for you guys to review. Remember, we have 5 homeworks, we have 5 group works, and we have those practice quizzes. There were actually just 3 of those. But those would be things that you could look at to help you study. And then, of course, there's also a sample midterm. So any of those things would be great over the weekend for you guys to work on. And the solutions to all of that stuff is posted. But you're also welcome to come by my office hours over the weekend. And if you got further questions about any of it, that's also totally fine. The way I usually do my review sessions, those of you who've been in my classes before, you probably know that the main thing I like to do is practice problems. I like to think of problems that maybe would be like what I would be thinking about for our exam. I didn't write the test yet, but I think I have an idea like what kind of questions I might want to ask. Before I actually do any of those problems, let me just say a couple of words of kind of wisdom about how to spend these next 3 days or whatever. The midterm is going to cover everything that we've done since day 1 of the semester, which is essentially chapters 2, 3, 4, and 5. And I was taking a look at it, and I really don't have a good breakdown among those chapters. I would say you should expect approximately an even distribution of questions across those 4 chapters. So approximately 25% of the midterm, for each individual chapter. Now, of course, some things cross boundaries between chapters. We've seen a lot of examples where, for example, we do the Chinese remainder theorem together with Fermat's little theorem. And so that's kind of going across between chapters 4 and 5. So I don't want you to take it too literally. I don't think that's such a good idea. If you're the type of person who needs structure when you're studying, take the midterm review packet because it has a list of all of the topics. And then there's a second list, it's a bullet point list of all of the things that you should be able to do for this exam. And I would recommend just go through it like a checklist and check these things off as you sort of figure them out. And if you get stuck somewhere, if there's something on that checklist that you're not comfortable with or you don't quite remember what it was about, then you can ask your classmates or you can ask me. And we can, try to get you straightened out on that. Okay, so definitely, if you like structure, that review packet is there for you. The questions on the exam are not going to just come in order necessarily. I don't like to put the hardest question right at the first page. That's kind of a little scary if I do that. So, I'm thinking a little bit about trying to make sure that some of the harder questions, maybe if I can think of it that way, that they might be towards the end a little bit more. But it doesn't always work out that way because what's hard for me and what's easy for me is maybe different than for everybody else. So I don't want to assume too much there. But you should assume that the questions are not going to come in order from the chapters. What that means is you need to get a little bit of practice with jumping around. This is why I have not been emphasizing homework as something to go back and rehearse a lot on, because the homework doesn't give you any practice on having to sort of be fluid between the different topics and the 4 chapters that we've covered, right? Because when you're doing problems in chapter 5, you pretty much know what chapter 5 is about, right? So you already have this massive hint before you even start. So I think it's fine to do homework, and you know, I want you doing the homework, obviously, but that's just tuning you up to get ready to tackle a test where the problems may be jumping around a little bit. So I think it's okay for you guys to do the same thing in your studying. When you're looking at the midterm, the sample midterm, right? Take that like it's a real exam and just set yourself down, and hopefully you'll get some practice with sort of having questions fired at you that may or may not be going in any kind of logical order. So just a little bit of advice about that. It is good to practice things sort of out of context, you know, where you're not just already in the mindset of one particular section of the book, because half of the challenge of some of these, not just this math class, but a lot of math classes, half of the challenge is just figuring out which of the many things that I have learned am I supposed to be using to do this or that problem. So, practicing that a little bit is actually a worthwhile thing. It's worth some of your time, I think. Okay. Also, remember, guys, this is a no calculator test. Now, I may have some questions on this exam. This is often the case with number theory. There may be some questions where if you just brute force it hard enough and long enough and persistent enough, you could actually do a lot of scratch calculations and come up with an answer. In number theory, of course, sometimes the answer is just a number that we're looking for. And you might be able to come up with that number through a elementary means by doing a lot of brute force calculations, okay? There's nothing wrong with that. I'm not the type of guy to sort of say, oh, you have to do it this way, right? I will usually ask a question and then allow you to solve it however you like. However, the thing you have to be careful about is that if you're going to say, well, you know what, I think I can brute force my way through this whole exam. I'm not ever going to use Fermat's little theorem or the Chinese remainder theorem. I'm just going to do it all kind of from scratch as if I've never been here. Maybe you'll be able to brute force something and get an answer, but you're going to use way too much time doing that. Okay, so when I'm gauging the amount of time that this exam should take, I'm assuming that you're going to use the tools that are available to you, right? And so if I ask you to calculate some massive power of a number modulo p, right? You could just start calculating powers of that number forever and just ignore Fermat's little theorem, and you might eventually get the answer, but you will eat up way too much of your time. So please try your best to think about the tools that we've learned. What are the skills that I've been trying over these last 5 weeks to sort of have everybody learn? Because those are the things that I'm probably going to be testing you on. I'm really not interested in just testing you on, you know, how well you're able to like take powers of a number or multiply a number out, something that you could have asked somebody to do, you know, who's a 6th grader. You just take scratch paper and work something out, right? I'm probably not going to be doing that. I'm going to be asking questions where the tools we've learned are actually helpful and that you actually are supposed to try to use those to be efficient and to work through the test. So just want you to keep that in mind. Some people, they study really well for these exams, and then for whatever reason during the test, they're just not primed and prepped in the right way to sort of do well, even though they've studied hard. So I just want you to have some advice about how to take a number theory exam, okay? Use the theorems, use the results, look at models of other problems that we've practiced on, and use all of those things to help you to do the problems on this test. This is not going to be a test where it's just all about doing a bunch of numerical calculations and let's just see who can do it the fastest, right? That's not what I'm interested in. So anyway, just a little bit of advice about the test in that respect. Okay, as far as the problems I'm going to show you today, I'm not going to talk about those theorems that you're, remember there's 5 theorems, 4 of them will appear on the test, and then you will have to write up 2 of those. I'm not going to go into any of that here because you guys know what to do for that. You need to review your book, your notes, whatever you're going to use as a source to try to learn those theorems. So I'm going to leave that part, which is probably about 25% of this exam is what I'm guessing I'll end up having it be. I'm going to leave that for you guys. I don't think we need to spend time on that in the review session. If you do have a question about one of the proofs, or maybe you have a slightly different way of looking at something that you'd like to maybe think about putting into your proof, sure, come by my office hours and ask me, and I'll be glad to help you with that. But for the most part, I think that just kind of going back to the book and to the notes and following along on that, you're going to do really well on the proof section of this exam. Okay, so I would rather focus on places where we need to be more creative, where scratch. Okay, so are there any questions before I go up to my board and I'm going to throw the first problem up and we're going to start working on some problems here. Does anybody have any questions after my little 10-minute overview here?
Yeah, I have a question, Professor.
Sure, what's up, Humberto?
Yeah, for the test you said, well, it should be enough time. Is the test made for enough time for the class time, or is that with the added time that you're giving us extra?
I'm going to make the exam so that I think that you can do the actual math and write out your solutions in that 75-minute block from 4 o'clock to 5:15. I'm not going to make the exam any longer than that in my head, right? But I am going to give you extra time so that you have a cushion for 2 reasons. One is it's a cushion so you have a little extra time to work. Maybe you make a mistake and you need to backtrack a little bit. I'd like you to have a little time to do that. And the second reason is because I know it's going to take people time to get their pages scanned, to get the exam, printed out if they're going to print it and get everything settled with the technology. So that's the reason, part of the reason I'm going to give some extra time. It's not because I'm going to write the test to be even longer than our regular class time. It's just that I want you to have a little buffer there.
Thank you.
Make sense?
Yeah, makes sense.
Okay, great. Any other questions before we start today, guys?
Yeah, Dr. And on the technology side, did you want us to set up like 2 cameras or something like that? Like
most people don't have 2 cameras, so do the best you can with whatever. I know it's not easy. Do the best you can with the technology that you have available, whatever that is, to set up your camera in such a way that I can see you and potentially even see sort of your workspace where you're doing some writing. I know that's asking a lot. Not everybody's camera is going to be able to do that. Do the best that you can with that. And if I am not happy with how somebody has set up their camera or whatever, I'll try to get your attention and ask you if you can sort of tweak it a little bit. Great idea to come in a few minutes early on Monday so that you can get the camera set up so that I'll already be happy with it and don't have to waste your time during the exam asking you to fiddle with your camera. That's another reason why it's a good idea to come early. Remember, I'm going to show up about 3:40 to 3:45 on Monday. I'm going to be there a good 10 to 15 minutes at least early so that I can just make sure that everybody's technology is fine. Now, if you can't come early, that's okay. I understand that. I am going to give extra time at the end as well. So there'll be time there to also work a little bit extra and scan things into the system. It's not a perfect system. I've been doing this now for almost 12 months and it doesn't work perfectly to give exams like this through Zoom, but it's the best we've got for now. So I'll try to be understanding and patient with you guys, and just to the extent that you can, do the best you can. Okay. Anything else? let me go up to my board and I'm going to throw a problem up there and let's try and solve it. Okay. So I've got a problem here in mind for us to work on. So here it is, and I'm going to number these problems right now. So number 1, it says this: find the 3 smallest positive integers satisfying, find the 3 smallest positive integers satisfying x is congruent to 11 mod 72 and 5x is congruent to 31 mod 52. So this is a system of congruences, okay? And you notice here that the moduli, the 72 and the 52, they are not relatively prime. And we didn't get a lot of homework. The book doesn't have a good emphasis on systems of congruences where the moduli fail to be relatively prime. So you didn't get a lot of homework practice on this. So I wanted to start today by doing this example so that we're practicing a little bit on how to handle this. So does anybody have a suggestion? And again, you can use the chat if you want, or we can use your microphone, whichever way. Does anybody have a suggestion what we maybe should do first here?
Can we break up the modules so they are prime?
Okay, so we could take the 72 and the 52. We could try to break, for example, 72 would break up as, 8 times 9. Those two numbers are relatively prime. And the 52 would break down as, I don't quite know, I guess 4 times 13, I think. And so we could do that. But ultimately, the fact that these two mods have some common factors between them means that even if we try to break down those mods, there are still common factors between those two. So there's something else I would actually recommend that we do even before we start working on the entire system here. Does anybody have an idea what I'm thinking of? What should we maybe do very, very first?
Can we show that the GCD of the mods divides 31 minus 11?
Okay, so let me just remind you, you're looking at the condition of whether there's even a solution to the system or not. But by the way, the fact that they're asking us to find the 3 smallest positive integers means that this system must have a solution. It must have at least 3 solutions. Of course, the question could have said, if possible, find the 3 smallest positive integers, right? So then you'd be in this quandary of, I wonder if there are any solutions or not. So let me just remind you guys that the condition, so if we have this system, this was the way I presented it in class, is we had a system that looked like this, and the condition for having a solution was that the GCD of n and m needed to divide a minus b. So actually in this particular case, well, yeah, in this particular case, I guess it is okay. But am I ready to use this yet?
It's the 5 in front of the 5x.
We need to deal with this first. Before we start asking about the 31 versus the 11, I need to look at this system down here. There's a 1 in front of the x's. So the very first thing I want to do is replace the second equation with a new one where we only have an x. We don't want to have that 5 there. The way that we can, handle that, remember that if you just take this second congruence, the GCD of 5 and 52, which is 1, by the way, does divide 31. So this second congruence actually can be solved for x. So this is kind of this problem has a couple of parts to it. The first part is to simply replace the second congruence with one that will fit the format of our system down here on the bottom, okay? So how do we do this? Let's just remember, we're gonna use the Euclidean algorithm. I'm pretty sure we're gonna need this on the test on Monday, right? Euclidean algorithm on 5 and 52. So I'm gonna take 52 and I'm gonna divide it by 5. It goes in there 10 times with a remainder of 2. Okay, then I'm going to take the 5 and I'm going to divide that by 2. It goes in there 2 times with a remainder of 1. So it's a pretty fast process, just 2 steps here. And now I'm going to run this algorithm backwards. So if I go backwards, I'm going to start with 1 and I'm going to write it as 5 minus 2 times 2. And then I'm going to take that second 2 and replace it with, from the first equation, 52 minus 10 times 5. And then finally, we need to do one more thing, which is we need to simplify this. And it looks like we have 21 factors of 5 minus 2 factors of 52. Okay, so this is the Euclidean algorithm forward and backwards. We're already seeing it on the very first problem. Now, we're going to be working in mod 52. So right now, I am only looking at this second congruence here. And in mod 52, obviously the multiples of 52 become 0. So in mod 52, this second term, we can ignore it. And that leaves me with just 1 being congruent to 21 times 5 in mod 52. So we're moving into the realm of a congruence equation now in mod 52. And what we know is that in mod 52, 21 will cancel 5, right? So that's actually what I want to use to get rid of this 5 right here. I'm going to multiply the second congruence through by 21, okay? So what we will get, so for the equation, I called it star up there, right? What we would get is 21 times 5x congruent to 21 times 31. All of this is still in mod 52, okay? And guys, don't hesitate to ask questions. The review is a great place to do that. We're not in really any hurry at all. The idea, though, is that the 21 times the 5 is just 1. So here's what x is equal to, okay? So I'm just going to simplify this then. X is congruent to 21 times 31. So we actually have to figure out 21 times 31. We're going to reduce that mod 52. Neither one of these numbers can be really made very small. You remember, sometimes you can use a trick where you just add or subtract 52 to one of these numbers to try to get some smaller numbers to play with. Here, that doesn't really help us very much because 21 and 31 are sort of both kind of halfway, you know, between 0 and 52. So if we try to replace these with negatives, for example, we're still going to have some big numbers in there. So it might just be easiest here in this case to come over on some Scratch and work out what is, and we'll do it without a calculator, what is 31 times 21. So we get 651. And so I'm just doing multiplication there. By the way, guys, if you mess up something like this, I know exams can be stressful. I hate them myself. And it's so easy. If you make a little mistake, you're probably nervous about what's going to happen to the problem, right? I'm going to continue to follow your work through. If you make a calculation error, but you continue to solve the problem by the right procedure with the right steps, I will be giving you pretty much almost all of the credit that I possibly can. I'm not going to take off a lot of points for somebody who miscalculates 31 times 21, right? This is not such an important thing. Okay. So 651, I have to divide it by 52. Let me come over here and do that. 651, this is another thing we have to do carefully. 651 divided by 52, it goes in there one time. And when I subtract 52 from 65, I get 131. And that goes in there two times, leaving 104. And 131 minus 104 is a remainder of 27. And that remainder is actually what we're looking for here. So in mod 52, x is congruent to 27. It's just this remainder. Okay, so far is everybody with me? Okay, so actually what I would like to do is, I'm going to erase a little bit. So I hope people are getting this copied down. If for some reason you're behind, I am going to post this video later, and you can obviously come back and kind of fill in any of the gaps that you may have. But what I basically want to do right now is come back up to where I have the star equation and put this down instead. Okay, so let me do that. I'm going to come back up to the top right here, and I'm just going to now replace this with x congruent to 27 mod 52. So Ben, you see why it's important. See, we want to be looking at 27 minus 11 rather than 31 minus 11. This is the actual number in the system of two congruences. These are the numbers we need to be paying attention to.
Yeah, as I was saying it, I saw the 5 and I was like, oh, okay, I don't think it's going to work like that.
Yeah, no worries. So the first step is to simplify that second equation. Now the GCD of 72 and 52 is actually equal to 4. You can check that pretty easily, right? By the way, if I give you some big numbers and I ask you to calculate their GCD, one of the best ways to do it is to actually just use instead of the Euclidean algorithm, you can just use a prime factorization. Just factor the two numbers into primes, and then the GCD is sort of the minimum prime powers for each of your primes. So you just grab the fewest powers of each prime that are common to both numbers. So you can do GCDs in two ways. You can do it using the Euclidean algorithm, but you can also do it just by prime factorizing it if you want to. That's if you have big numbers. Here, you can almost just do it in your head. It's not that hard to come up with the GCD. The point here is that GCD does divide 27 minus 11. 27 minus 11 is 16, and 4 divides that. So this system does have a solution, right? This is a system that has a solution. Okay, so let's start working on it. How do we get the solutions here? Okay. Well, in the class, let me write down the system one more time. X congruent to A mod n, and X congruent to B mod m. D is the GCD of n and m. You may remember this is the problem where there's all this alphabet soup of letters. And so I'm going to remind you that we also had a number called t. T was just a minus b divided by d. All right. And then we also wrote d as an integer combination of n and m. So if you remember the notation from the class, the d, of course, can be written as n times something plus m times something. So there's an r and an s for that. So we have A, B, M, N, D, T, R, and S. There's a ton of letters here. You're going to want to, maybe you need some flashcards, or you just need to memorize this, how all these notations work. But essentially, the solution for x is that x is equal to a minus nRT, or you can use b plus MST. So either one of these, but this should be in your list of things to study over the weekend, making sure you know for a system of congruences where we have two mods that are not relatively prime, so we're not using the Chinese remainder theorem here, we can get a solution and either one of these is the same. These will come out to be the same actually. Okay, so let's write down what these variables are in our example. For our problem, A is 11, B is 27, N is 72, M is 52, and then we have D, which is actually just 4. T is just A minus B divided by D. So we just look here, A minus B is negative 16. Divide by 4, we get negative 4. Okay, and then the only other numbers that we have to come up with are the R and the S. So, and write it as 72 times R plus 52 times S. Okay, so we kind of have to figure out what R and S are. We do that by using the Euclidean algorithm forwards and backwards, right? So we have to, I guess we can do it one more time, practice this one last time. So we're going to take 72 and 52, and we're going to try to work out the greatest common divisor and run the algorithm forwards and backwards. So there's one factor of 52 here, plus 20. Okay, so 72 is 1 times 52 plus 20. Then we take the 52, that's 2 times 20 plus 12. Okay, and then from there we take 12 and divide it into 20, and it goes 1 time with a remainder of 8. And then finally we take 12, 8 goes in there 1 time with a remainder of 4. And we already know that 4 is the GCD, so that's going to be the last step. And now we have to run the algorithm backwards. Okay, so maybe, is it okay if I skip that? If I just kind of tell you what the R and the S are going to be, would you be willing to take that from me? Just to save a little time. Yeah, this part is not so bad. We just start with 4 and we work backwards through this Euclidean algorithm. And what's going to come out of it, because I did this earlier, is that you're going to get negative 5 times 72 plus 7 times 52. Be a little bit careful, guys, that you might have written the 52 first and then the 72. Because it's just a combination of two numbers. You may have had it in the opposite order. Just make sure you don't get mixed up about which of these numbers is R and which one is S. The R goes with the N. In this case, N is 72. So R is going to be negative 5. And S, which is the coefficient of M, well, that's just 7. Okay, so those are all of the numbers that you need to now plug either into this one or into this one. If you plug the numbers into both, you can check if you did it right, because you should get the same number for A minus nRT as you do for B plus MST, right? So those should both come out the same. And so I'll just use the first one here. This comes out to 11 minus N was 72, R was negative 5, and T was negative 4. Okay. Let's see, 5 times 4 is 20, and 20 times 72, that's just 72 times 2 with an extra 0 on the end of it. That would be 144 with an extra 0 on the end of it. So this is 11 minus 1440, which is actually negative 1429. Negative 1429. That and if you try the B, the M, the S, and the T, you'll get the same value. By the way, guys, I give partial credit for every little part of this problem. If this was on the test, this would probably be at least a 12 or 15 point problem. You're going to get points for all of it. So if you get stuck and you don't finish the whole thing, don't just erase it or not scan it or something like that, right? Make sure you let me look at it. I might find some points for you there, right? So it's always good to turn in as much as you can. Are we done? Is this the final answer?
I have a question.
Okay, so Ben, go ahead and ask your question, and then I'm going to ask you guys again whether we're done or not. Go ahead, Ben.
Okay. Would it be different if we did t equals positive 4 instead? Like, would it either one work? If we did b minus a over d?
This needs to be a minus b over d. If you switch if you switch this to b minus a, you're basically switching the roles of the a and the b here, and it throws things off a little bit. You would get a different answer. So
okay, but when
this is actually a very sensitive type of problem where the numbers have to be kind of very carefully calculated. The nice thing about this, guys, is it's totally computational. If you just learn what you need to learn to figure out the numbers A, B, M, N, D, T, R, S, you're going to get it right every single time. Okay, so that's the good part of it. It's not terribly heavy on the theory side, but we do need to follow this rubric pretty closely.
Okay, and then earlier when we were showing solutions using the GCD, we did b minus a instead of a minus b. For that part, it doesn't matter, or?
That doesn't really matter. Yeah, that does not matter. Yeah, because if you, if you pick the, like if I say I'm going to take 11 and divide it by 17, well, basically what happens is you end up with a quotient of 0, and then the remainder is just 11 here. So then on the next step, you put the 17 over here and the 1 times 11, and you basically just switch. You have one extra unnecessary step if you put them in the wrong order, but you'll end up getting the same steps after the first one, and you'll get the same answer for the GCD. Yeah, that's a good question. Yeah, you bet. So guys, am I done right here? No, we need to find the 3 smallest positive integers. Exactly, so this is a negative answer. So that's not what we're looking for. However, if you're running out of time on Monday's test and you have to turn something in, turn this in, because honestly, we've done at least 85% of this problem already. And so you would get that much partial credit even if you wrote this down as the answer. I mean, we know it's not correct, but it's a long way along the process of getting to the correct answer. So you should let me know that. You should definitely submit it and let me look at it. But no, we need to go a little bit further. There is a uniqueness statement to this system of congruences, and that is that the solution is unique modulo the LCM of 72 and 52. So let's look at the LCM of 72 and 52. By the way, guys, one way to figure out the LCM, do you guys remember this? If I take A times B, it's equal to the LCM times the GCD. You guys remember that? So if we already know that the GCD is 4, and we just multiply 72 times 52, we can solve for the LCM. So this is a nice little equation here. So this is just going to be 72 times 52 divided by 4. And I guess I should have put this down here where I have more room. If I just take the If I just take the 72 and I divide it by 4, I get 18. So this is really just, this is just equal to 18 times 52. Let me just work that out kind of as a quick little scratch calculation. 18 times 52, we have 36. And then we have 900, so 936. So this is 936. Okay? So the solution to our congruence is unique modulo 936. What that means is that we can take the solution that we found and we can add and subtract 936 as many times as we want. Now, if I add 936 the first time, I'm still going to have a negative number, aren't I? Negative 14 something, we add 936 to that, it's still negative. So I need to add at least 2 multiples of 936. So if we take 936 times 2, 936 times 2, we're going to get 1872. Okay, that's a big enough number that when you add it to negative 1429, we'll get a positive value. So let's add that to negative 1429. Effectively, we end up having to do a quick little subtraction here. We should get, if I did it right, 443. So this negative 1429 is congruent to 443. This is in the mod of 936. And then we just have to add 936 a couple more times, right? So we take 443, we add 936, and we get another solution, which would be 1379, right? Or we can add another 36, and we're going to get 2315. So these would be the 3 smallest answers: 443, 1379, and 2315. That would be what we were looking for. Took a little doing, but that's the solution. Is everybody okay with that one? I wanted to make sure to do one of these because you really didn't get as much of this in the homework as it would have been helpful to have. So I thought it was worth showing that to you. Okay, let's maybe move on to another problem then. Can I erase?
Dr. Annan?
Yeah.
For when we write the answer to this, do you want 443 mod 936 and then 1?
No, actually, we don't even need the mod. All it says is find the 3 smallest positive integers. It's just these 3 right here.
Okay.
Okay, let's do another example. Let me come back up to the top here. Okay, so this is number 2. You have $1,358 to spend on pet adoptions. This is a word problem, guys, so bear with me while I write it down. $1,358 to spend on pet adoptions. It costs $35 to adopt a cat, and it costs $133 to adopt a dog. Okay? So then the question is just going to ask, well, how many dogs or cats can you adopt? Like, what are the choices? Okay? So what possibilities what possibilities are there for the number of cats or dogs, sorry, cats and dogs to adopt? Okay, so I'll give you guys a second to write that down. I'm going to erase the rest of my board here. Okay. Can anybody tell me what does this problem have to do with? What's the topic here?
The Diophantine equation.
Very good. Yes, Ben. This is a Diophantine equation problem. It's just being phrased in a word notation. But the idea here is to basically try to set up a Diophantine equation. And of course, we've learned how to solve those. So this is a good chance for us to practice this. You shouldn't be surprised that I will probably have something on the test that is an actual application, like a real world application of number theory, some kind of a problem that is where we use what we've learned to solve a real problem. And this is an example of that. Okay. So if we want to solve this using Diophantine equations, we have to come up with an equation and we need variables. Can somebody help me? Like what kind of variable, what would be the variables that we would need to be representing here?
C and D.
C and D, Christine, for the number of cats and dogs, right?
Mm-hmm.
Yeah, that's exactly what I would do. So let's just do this. We'll just let C is going to equal the number of cats. And D is going to equal the number of dogs. Okay, and we would like to find what are the possible combinations for C and D. We do know that every single cat costs $35 and every single dog costs $133. So we can actually make that into an equation already. 35 times the number of cats plus 133 times the number of dogs. And that should add up to the total bill, how much money we're spending on adopting these animals. And that's given to us as $13.58. So we can go ahead and put that up here as well. Okay, so actually this is our Diophantine equation. And we just need to remember that C and D have to be whole numbers and they cannot be negative numbers. So as we're working this out, if we come up with fractions or if we come up with negative numbers for C or D, we're going to ignore those. We have to be looking at values that are at least 0 here. Okay, fantastic. So the first thing I usually like to do, by the way, with these Diophantine equations is make sure that I really cannot reduce them at all. Actually, you might notice that 35 and 133, they do have a common factor in them, which is 7. If you need to, just take a minute to factor these numbers. Okay, so, we have divisibility tests that we learned in this class for a number being divisible by 2 or 3 or 4 or 5 or 6. We didn't have one for 7, but you can quickly figure out that there is no common factor of 2, 3, 4, 5, or 6 just by looking at the two numbers that you have here. The first one that has a chance of being a common factor other than 1 itself is the number 7. And 7 does go into 133. So the GCD of 35 and 133 is 7. And now the question is, does that divide 1358? Because if it doesn't, then there's no solution here. Remember, a Diophantine equation might not have a solution if the greatest common divisor of the coefficients of the variables If it doesn't divide the right-hand side, then there's no solution. Well, if we take 1358 and we divide by 7, let's see, it goes in one time, we put 7 here, we bring down 6. 65, that goes in 9 times. We put 63 here, bring down 2. 28 goes in there 4 times. Sure enough, this 1358 is a multiple of 7. So what I would actually recommend that we do is just divide the whole thing through by 7 to begin with. Let's make these numbers smaller for ourselves, okay? If we divide the whole thing through by 7, we don't gain or lose any solutions, right? We're still going to be solving the same values of C and D. So I'm going to divide by 7 on my original Diophantine equation. Let me just write that like this. I'm going to divide by 7. It's going to leave me with 5C plus, when 7 gets put into 133, it goes 19 times, I believe. You can check that. And 1358 divided by 7, we already figured. Okay, so now the new equation has some friendlier numbers in it, some smaller numbers, and the GCD of 5 with 19 is just 1. So that's really, really handy. Okay. Can somebody tell me, what am I going to want to do next? I just basically gave it away, right? Sergio, do you have an idea?
Want to find the general solution? So you're gonna find C and D by using the Euclidean algorithm
Okay, I got to use the Euclidean algorithm on what 2 numbers?
on 5 and 19.
Exactly. I'm going to take 19 and 5, and I'm going to use the Euclidean algorithm. So I take 19, I divide it by 5, it goes in there 3 times with a remainder of 4. Then I take 5, it goes in 1 time into 4 with a remainder of 1. So that's pretty easy. We just have 2 steps to get the GCD, which is 1. Now I'm going to run it backwards. So 1 is going to equal 5 minus 4, but that's 5 minus 19 minus 3 times 5. So I can go ahead and put that in there. And now I'm just going to combine my 5s together here, and I have 4 factors of 5. This is 4 factors of 5 minus 19. 4 factors of 5, that's 4 times 5 there, guys, if you can't read that. 4 times 5 minus 19. So basically we have, let me write it over here. We have 5 times 4 plus 19 times -1 is equal to 1. Okay, this is our equation that we just figured out from the Euclidean algorithm. The next thing I'm going to do is scale this up to get my 194 right here. Yeah? So I have a 1 on the right-hand side of my equation right now, but I need to have 194 there. So I'm now going to multiply. I'm going to write that as a dot. I'm going to multiply right now by 194. But be sure to put the 194 with the numbers that are in the parentheses. Don't power up the 5 and the 19. We don't want to do that. We just want to put the 194 with the 4. So I need to figure that out. 194 times 4. If I just calculate this again, I'm trying to do it without a calculator. I should get 776. So we get 5 times 776 plus 19 times -194 equals 194. Okay, so we've just multiplied through by 194. And now we actually do have a solution to our Diophantine equation here, which is C naught, I'm going to call it C naught, is 776, and D naught is negative 194. So we have those two numbers, 776 and negative 194. I'm going to call those C naught and D naught. This is a solution to the Diophantine equation. The problem is it's not an acceptable solution. I cannot have a negative number of dogs here. Okay, so what I have to do is I have to remember how to generate this infinite family of solutions. So this is another equation everybody needs to sort of put on a flashcard or something. Try to get this one memorized. That there's actually a generic equation for C and D. Namely, C naught, which is 776, and D naught, which is negative 194. That forms the original solution. And then what you do after that is you add B over D times T, and you subtract A over D times T. So T is the parameter here. And in this system, the D is just 1. I actually shouldn't have erased my equation quite yet. So here's the equation, just to get it back up here one more time. So the D is just 1 once we're looking at this equation. The 5 and the 19, they are relatively prime. And the A and the B are just the 5 and the 19. So this is going to be 776 plus 19t. And the second equation is negative 194 minus 5t. Okay. So we actually now have not just one solution for the number of cats and dogs, we have an entire family of them. And the important thing is that both of these expressions here on the far right side of my board have to be not negative. So I have to have 776 plus 19t at least 0, and negative 194 minus 5t at least 0. The number of cats and the number of dogs, they both have to be at least 0. Okay, so just stop me if there's any questions so far. What I'm going to do with these two inequalities is I'm going to use them to create sort of a range of t values. Because the first inequality actually tells me that t is greater than or equal to, I'm going to subtract the 776 over and then divide by 19. Negative 776 over 19. That's the first one. Okay, and then for the second one, I'm going to do something similar. Sorry, just a second. I've got to wake up my computer here really quick. So for the second one, I'm going to do something similar. I'm going to also solve for t again. And the second one is going to tell me that t is less than or equal to negative 194 over 5. So if you just isolate the t in both cases, this is what you're going to get. Well, as I look at it now, those numbers are not the friendliest numbers in the world. To, like, those are fractions that we would have to solve for. It's not terrible to solve for them, but just so you know, essentially there are only two values of t, which are negative 39 and negative 40, that satisfy both of those. So you can tell that they are negative, right? So basically, negative 776 over 19 is less than or equal to t, which is less than or equal to 194 over 5. So if you actually divide these out as fractions, you'll see that the only integer values of t that are between these two values are negative 39 and negative 40. And so from there, we're going to just take both cases. So if t is negative 39, then I can come up here and into my equations and solve for C and D. I'm just going to tell you what we're going to get to save a little time here. It turns out that if you plug in negative 39 for t, you will get C equals 35 and D equals 1. So that would be 35 cats and 1 dog. That's one possibility. The other possibility, which is with t equals negative 40, for this one, you would come up with 16 cats. So C is 16 and D is 6. So there would be 16 cats and 6 dogs. These are the two ways that you can spend exactly $1,358 on dogs and cats with these prices. So there's a little bit here that the numbers are a little bit tricky. Try not to get too worried about it during a review session. Sometimes during the review session, I don't have numbers that are always perfect. For the exam, of course, I will make sure that the calculations are not going to be crazy to do. Because here, for example, to find C, you have to take 776 plus 19 times negative 39. That's a little bit of a headache to do that one. So try not to let that bother you. Focus more on the process, making sure you understand how we came up with these two possibilities. Everybody with me? Any questions on this one? Okay, great. Well, I just wanted to practice something where we could use Diophantine equations. We've done some linear congruences already, so it's good things to be practicing. Let's move on to another example. All right, I have another problem here that's hopefully a good problem to work on. So let's do this one. This is number 3. Find the remainder So find the remainder when we take the number 3 and we're going to raise it to the 999,999,999, right? When that is divided by 168. Okay, so I don't think a calculator is going to help us here, even if we had one. And I like problems like this where the calculator pretty much is useless. These numbers are way too big for us to use a calculator. So why don't you spend a minute, think about what you might want to do here. Three to the 999,999,999. We're going to divide that by 168, and we're going to ask, what is the remainder? The correct answer is, of course, something between 0 and 167. Right? Your possible remainders have to be within that range. Any thoughts on what to start off doing here?
Um, can we start taking powers of 3 and trying to see where that number mod 168 might be a nice little number?
You know, maybe we'll get lucky. Swan, I like your thinking. Maybe we'll get lucky. We take 3 to some power along the line, and magically it comes out to something like a 1. Like you get like a remainder of a 1. But is there another idea?
Could you break down 168 to its prime factorization and then find the, I guess, in those mods and then do the Chinese remainder theorem?
Okay, so I love that idea, Sergio. The thing here, guys, is that we're trying to calculate a large power of a number. That should make us think of Fermat's little theorem. Fermat's little theorem says that a to the p minus 1 is congruent to 1 in mod p. Now, the thing is, we don't have a prime here. So this is what Sergio is suggesting. He's saying, let's factor 168 into its prime factorization. Now, when we do that, what will happen is we will get 3 times 7 times 8. So the turns out that it does not just factor into separate prime factors. We have 3, 7, and 8. But I love this idea. Let's figure this thing out mod 3. Let's figure it out mod 7. And let's figure it out mod 8. And then use the Chinese remainder theorem. These numbers are relatively prime. So I can do the CRT once I've figured it out in mod 3, mod 7, and mod 8. So can somebody help me out? In mod 3, what is this number that we're looking at, this massive power of 3? What is it going to be congruent to in mod 3?
0.
Exactly, it's just 0, right? 3 is the same as 0, so this is just 0 right here. Okay, now let's look at mod 7. Now for mod 7, it's a little trickier because 3 is not the same as 0 in mod 7. But what we can do is just use the Fermat's little theorem. Fermat's little theorem says that we can raise 3 to the 6th power and it becomes 1. So what I can do is I can say, let's take 3 to the 999, 999, 999, and let's put it into 6 packs. Because if we put the 3s into packs of 6, they cancel every single time. So this is going to be 3 to the 6 to the something. So what you actually need to do is divide 999, 999, 999 by 6. And see how many factors of 6 will go in there. It turns out you can fit in 166,666, sorry, 166,666,666. You can fit all of that in there with, I need a little more room here, guys, with a little leftover amount, which is 3 cubed. Just to make sure that everybody's following what I'm saying here, right? You're going to need to take 999, 999, 999. You're going to divide it into 6, right? Because that's how you're going to figure out how many 6 packs you have that can be canceled out. So you divide this thing into 6, and that's where this 166,666,666 comes from, with a remainder of 3. So you do need to do this little scratch calculation. And using that, essentially the division algorithm on that right there, you now know how to break this 999,999,999 as 6 times something with a remainder of 3 over here. So make sure you're breaking down your exponents correctly on this. But the point is that this is actually just 3 cubed, which is 27, and we're talking here about mod 7. And in mod 7, well, 27 is the same as -1. So in other words, guys, this whole big massive thing right here is just 1 in mod 7. 3 to the 6th is congruent to 1 mod 7. Okay? So this is by Fermat's little theorem. I'm not being as organized on this board as I wish I was. So our number is congruent to 0 mod 3 and it's congruent to -1 mod 7. Now we have to look at mod 8. Okay, so we're going to go 3 to the 999, 999, 999. And now I'm going to put mod 8 over here. The issue with this one, of course, that you have to be careful, 8 is not prime. So I cannot use the Fermat's little theorem for this line. Fermat's little theorem is only when the modulus is prime. So we have a mod 8 and we have to live with it. This is what we have here. So if we're not going to use the Fermat's little theorem, then I think the next best bet is to go back to Tuan's idea. And in mod 8, it's not so terrible. Tuan, you were originally trying to do this with the original mod 168. That's a little tough. But mod 8 is not so bad. And in fact, what is 3 squared?
1.
It's just 1 in mod 8, right? So actually, this becomes quite easy. You're just going to get 3 squared to some power. I'm just going to put a number there. And then I know there's 1 extra 3. Basically, there's an odd number of 3s. So this is 3 squared to the whatever. You just have to divide this. I guess it would be 499,999,999. But anyway, the point is that it's 3 squared to the something times 1 left over 3 here. And 3 squared is just, by luck, it just happens to be 1 in the world of mod 8. And so we end up with 3 right here. Okay. So guys, what this tells us is that this number that we're looking at, 3 to the 999, 999, 999, that number satisfies the following system. X is congruent to 0 mod 3. X is congruent to -1 mod 7. And X is congruent to 3 mod 8. So to just write it as a congruence there, that's what you would have. X is congruent to 0 mod 3, -1 mod 7, and 3 mod 8. And so Sergio's idea of using the Chinese remainder theorem now is a great one. Guys, this is almost certainly going to be on the test. I know I haven't written it yet, but a problem where you have to use the Fermat's little theorem together with the Chinese remainder theorem. This is a classic use of 2 huge number theory results. So you should be expecting something like this, right? This is basically what's going on. So this one now, this is where we use the, the A1, N1, Y1, A2, N2, Y2, and so on. So we would have, in this case, A1 is 0, A2 is -1, and A3 is 3. Capital N1 is 56, capital N2 is 24, and capital N3 is 21. So we can write those numbers down. I hope everybody understands where I'm getting these from. The capital N's are the product of the other two mods. So capital N1 is actually the second and third mods multiplied together, 7 times 8. That gives me 56. Can you guys all read this? It's a little bit smudged on my screen. It says 56 right here for N1. And then N2 is just going to be the 3 times the 8, which is 24. And then N3 is going to be the product of the first two mods, which is 3 and 7, which is 21. Okay? And then we have to find the Y's, Y1, Y2, and Y3, right? So remember that if we take capital N1, so I'll just say next, capital N1, which is 56 times Y1 is congruent to 1 modulo 3. Okay? And then while I'm at it, let me write down the other ones. 24Y2 is congruent to 1 mod 7. And finally, 21Y3 is congruent to 1 mod 8. So we're going to solve for the Y1, the Y2, and the Y3. These mods are really small. I can very easily do them without a lot of headaches because I can reduce my numbers. Like the 56, 24, and 21, I can make those much smaller if I work in mod 3, 7, and 8, right? So 56 in mod 3, if you just work it out, is the same as 2.
Dr. Annan,
Yeah.
would we even need Y1 since A1 is 0?
Oh, good point. Yes, you're right. We don't actually need to know what Y1 is. Thank you. I'm doing work I don't need to be doing. But yeah, that's what you would do. 56 becomes the same as 2. And then from there, you can solve for Y1. Y1 is going to be equal to 2. But you're right. We don't actually need to know that value, but just in case anybody's curious, that's what it is. In mod 7, 24 just reduces to 3. So this becomes 3 Y2 congruent to 1 mod 7. And we can just, this is a linear congruence that we can solve by doing the GCD business with the Euclidean algorithm, but you don't need that here. In mod 7, honestly, you just have 7 choices. You can try all of them in for Y2 until you find the one that works. And there will always be one that works because that's how this Chinese remainder theorem is supposed to work. So there has to be a solution, and you can see that it's equal to 5. 3 times 5, which is 15, is the same as 1 in mod 7. So I'm just going to write that down. I'm not going to derive it in detail. Y2 is congruent to 5 in mod 7. And then lastly, I have to take 21. In mod 8, it reduces to 5. So this is going to be 5Y3 congruent to 1 mod 8. And again, there has to be a solution for Y3. And there's only 8 choices, I guess, of what that solution could be. And so you can just kind of run through the numbers and you see that Y3 is 5. 5 times 5 is 25, which is the same as 1 in mod 8. So we'll just put that down here. Y3 is also 5, but this time we're talking about mod 8. Okay, so we have the numbers that we need. And so what we get is that from the Chinese remainder theorem, X is congruent to, well, A1, N1, Y1 is just 0. And then A2, which is -1, N2 is 24, and Y2 is 5. And then A3, which is 3, N3, which is 21, and Y3, which is 5. Okay? And I'm just going to work out what that is. Numerically, let's see, we have negative 120 here. And then what is 21 times 15? 315, I believe. So 315, and if you work that out, you get 195. And the thing is, guys, that we are getting a solution modulo 168. So if I ask you what's the remainder, you're not going to tell me 195. You're going to need to reduce this to a number between 0 and 167. So what you would need to do is say this is congruent to, what is it going to be, 27? Yeah, in mod 168. So the remainder should be a number between 0 and 167. And in this case, the answer is 27. So we get 27. That should be the, I'm going to just check my solution to this and make sure that's what I got. Yep, it's exactly what I got. Okay, fantastic. Any questions on this one, guys? It's a great combination of Fermat's little theorem and the Chinese remainder theorem. So we've studied some linear congruences. We've studied some systems where the mods were relatively prime or not relatively prime. We've done some Diophantine equations. It's all been computational so far. But guys, on the midterm, there will be some theoretical questions. Like I will ask you to prove some things. And I mean, in addition, you're going to be proving the theorems that you're learning, but there will be other things to prove as well. So this exam, you should expect a mix of the kind of problems we've just been going over with a lot of calculations and running through the sort of the algorithms and the procedures, but there will also be some more theoretical problems. And I'd like to show you some examples. It's very hard, to give like every theoretical problem is different. So when you're watching me do these theoretical problems, and as we're working on them now, I don't want you to think, oh, okay, so this is what he's going to ask us on Monday, because it won't be exactly the same. Like I will ask theoretical questions that are similar in terms of difficulty and length and style and things like that. But try not to take this review session too literally. One of the mistakes that I think sometimes people make is they come to my review sessions and they follow everything and say, yep, I get it. But they're too just glued into the problems that we actually just did here rather than sort of the big picture of everything. So as I'm doing some more examples now, just bear that in mind that I'm going to be doing some theoretical problems that use tools we've learned. But you're going to have to do different problems on Monday. And so it's important that you not only understand what we're saying here in the problems I'm going to do, but that you are sort of sharpening your own skills at these kinds of problems in general. Okay. And we've had quite a few theoretical problems as well throughout the semester in the group work, in the homework, and in the sample test, you'll see it too. So let me throw one up here. Let me give myself some room. So this is going to be problem number 4. And what this says is let A, B, and C be elements of the positive integers. So we're going to take 3 positive integers, A, B, and C. And what I'm going to ask us to do here is prove that the GCD of A with the the GCD of B and C, okay, if that makes sense, is equal to the GCD of A and B with C. Okay, so I've put the parentheses in here kind of carefully to keep this a little bit straight, what we're looking at here. So if we first calculate the GCD of B and C, and we take that number and then take its GCD with A, we should end up with the same thing as if we first take the GCD of A and B, and then take that number and combine it with C and take the GCD of those two things. Okay, so let's think about this a little bit. Let me give myself a chance to erase here. So I did talk about this, it's been a few weeks, and so this is a chance to sort of trigger your memory about this again. Whenever you have an equation where you are proving that two GCDs are the same, the trick really is to just show that you have the same common divisors of the two things on the left, in this case A and this GCD of B and C, and the two things on the right, that they have all of the same common divisors. If that's true, if they have the same common divisors, then the greatest one of these common divisors will agree with the greatest one of these common divisors. So this is kind of the right way to approach this. So let's write something down that would get us sort of on the direction of the proof here, okay? So for the solution, suppose that D is a common divisor of A and the GCD of B and C. So we take something that's a common divisor of what's on the top line. So this means that D divides A and D divides the GCD of B and C, right? Let's write that down. So what we know is that D divides A and D divides the GCD of B and C. It's a common divisor of both of those things. But if D is a divisor of B and C, then doesn't D have to divide B and also C? Yeah. D divides a number that itself is a divisor of B and a divisor of C. So by the transitivity of division, of divisibility, D actually has to divide B and C. So by transitivity of, I'm going to just draw a bar for that. So by the transitivity of the bar, right, D divides B and D divides C. So it divides A already, and now it also divides B and it also divides C. So D divides all three of the numbers that we started with. In particular, D is a common divisor of A and B, which means it has to divide the greatest common divisor of A and B, right? So if you have something that's a common divisor of two numbers, it always divides the greatest common divisor of those two numbers. So let's write that down as well. Since D divides A and D divides B, D divides the GCD of A and B. So D has to divide the greatest common divisor of those two numbers as well. Okay. And so D is actually a common divisor of, so D is a common divisor of the GCD of A and B and C. It divides both of those two things. So it's a common divisor. That's all that means, right? It's a common divisor. So in other words, guys, anything that divides both of the two things on the top line also divides both of the two things on the bottom line. Anything that's a common divisor of the two things on the top is also a common divisor of the two things on the bottom. And now I'm just going to say, similarly, divisor of the two things on the bottom, it would be a common divisor of the two things on the top. So let's just say, conversely, if D is a common divisor of the GCD of A and B and C, then by a similar argument, D is a common divisor of A and the GCD of B and C. So we don't need to write that all out as a whole proof again. We can just say by a similar argument, if D divides both of the two things on the bottom GCD expression, then it divides both of the two things on the top expression. Okay? This tells me that the collection of all common divisors of the two things on the top is the same collection as all of the divisors, common divisors of the two things on the second line. And so that means that the greatest one of all of the things on the top list matches the greatest one from the list on the second line. Okay, so thus, we can just jump to the conclusion then. Thus, the GCD of A with the GCD of B and C is equal to the GCD of the GCD of A and B with C. There we go. Sorry, I know it's a little, I don't know why my lighting is a little off today. I guess it's because it's later than our normal class. It gets dark at night over here about this time, so. Readable? So this is kind of a proof. This takes a little more writing to kind of justify this one. No question about it. Okay, let's do another one that's kind of on this theoretical plane. So by the way, the lesson that you should be taking away from this, guys, is not so much all the details of this particular problem, because I'm probably not going to ask you this particular problem on Monday. But what you should be taking away from this is that if you see a question where I'm asking you to prove that the GCD of one thing is equal to the GCD of another thing, that this is the strategy. Take a common divisor of, the first thing and show that it's also a common divisor of the second thing. And conversely, if I start with a common divisor of the second thing, usually by a similar argument, it's also a common divisor of the first thing. And therefore, you can jump to your conclusion at the end. It's that framework that you should take away from this problem and be ready to use on another example, more so than to like memorize dotting every I and crossing every T of this proof. Okay, but it is good to understand it, obviously. And if there's anything that's not clear here, let me know. I get excited and I forget to stop and turn around and make sure everybody's okay with it. Okay, let's go on to another example of something maybe a little more theoretical. By the way, don't get scared too much about the theoretical problems. I'm not going to make them, a massive part of the exam, and I may give you some choices. I may say, and you'll see this on the sample test, choose any, 3 out of these 5 or something like that. And so maybe a particular theoretical item won't hit you quite right, or you don't quite have the idea what to do. You can let that go and maybe try something else. Okay, so just be aware that is probably going to be the case. I'm not going to be pinning you guys into doing like a whole lot of high point valued theoretical problems where you have no way out. Okay, that's just not very nice for me to think about doing that. Okay, so let me throw another one up here. Okay, so let me write it down and then I'll erase the rest of my board. So here's what it says. This is number 5. Let n be a positive integer. So we take a positive integer n and suppose that p is an odd prime divisor of n squared plus 1. Okay. Prove. Okay, so p is an odd prime that divides n squared plus 1. Let's prove that p has the form 4k plus 1 for some integer k. Okay. So we'll do that. Let me erase my board here. Now, of course, p is an odd prime. So it either has the form 4k plus 1 or 4k plus 3. We're trying to prove that with the given assumptions, p actually has to be of the form 4k plus 1. That's what we're going to try to do right now. So do we have any results that you guys can think of that involves like concluding that a prime has the form 4k plus 1? We've got a couple things in the chat here. There's the fundamental theorem of arithmetic. The fundamental theorem of arithmetic is that really important theorem. It's actually one of the ones in the list of proofs. It's that result that basically allows you to factor every integer, every positive integer, uniquely as a product of primes. Okay. It doesn't really get into whether the primes are, 4k plus 1 or 4k plus 3, or whether they could even be 2. But it is certainly related to prime factorizations. So that's certainly something we can take a look at. The division algorithm is another tool that, of course, we have. The division algorithm doesn't really talk a lot about primes, though, and what kind of form those primes might take on. So that's certainly not, all of these things I'm reading in the chat sound like great ideas, But what's coming up the most often in the chat is theorem 5.5, which is really the key. This is really the key. Do you guys remember? This is the theorem we just did this past week, or this current, I guess it's still this current week. So on Monday, we proved, we were talking, yeah, Salma typed it into the chat for everybody to take a quick look at, which is nice because then I don't have to write it down. If we take the congruence x squared plus 1 congruent to 0 in mod p, this is if and only if p is congruent to 1 mod 4. In other words, there's a solution to this congruence if and only if p is congruent to 1 mod 4. So the thing is, if p is an odd prime divisor of n squared plus 1, so let's write that down. I'm just gonna, I don't necessarily have the full idea quite yet, but let's just write down the idea here. P is a divisor of n squared plus 1. Doesn't that just mean that n squared plus 1 is congruent to 0 in mod p? This just means in mod p, n squared plus 1 is congruent to 0. And that looks to me like what we're saying is that n is a solution to the quadratic congruence that Salma has in the chat, right? So this tells me that n is a solution to x squared plus 1 congruent to 0. And that's in mod p. So I'm just basically rephrasing, you know, what this says, what we have up there so far. And so that pretty much tells me if we have a solution to this quadratic congruence, that pretty much tells me that p has to be congruent to 1 mod 4. So by theorem 5.5, p is congruent to 1. Yeah, that's what I meant to say. P is congruent to 1 mod 4. Okay, so you basically can immediately use that theorem. And in other words, this tells me that p is equal to 4k plus 1 for some integer k. Yeah, that's basically the idea here, guys. So the trick here is to getting the right tool, which is what Salma has in the chat, right? The thing that's currently sitting in the chat. Recognizing that, I want to prove that p is congruent to 1 mod 4. Do I have any results about that? And when you look at this n squared plus 1, it's supposed to remind you of x squared plus 1 congruent to 0 in mod p. So this is another reason why it's kind of natural to look at theorem 5.5. Okay, so that's a good theorem to have on your, on your flashcards or whatnot. We are going to be talking more about more general quadratic congruences later in the semester. So this is just sort of the foundational building block right now. And I do want people to know it is a very useful result. So I won't be asking you to prove this theorem. Theorem 5.5 is not one of your 5 big theorems to be able to prove, but it's still a good theorem to obviously to know and to sort of recognize when to use it. Okay. So far, so good, everyone? Okay, great. I've got a few more here I want to do, some more theoretical examples. I have some pretty good theoretical problems. Let's try this one right here. I think this is number 6. Is that correct?
Yeah.
Okay, perfect. Let's do number 6. This one is very short to write down. So let's try to prove the following. If we take 4 times 29 factorial, and we add 5 factorial to that, this is divisible by 31. This one may not look so theoretical because it's got like a specific set of numbers in it. So it seems like it could actually be computational, but it is a proof. And so this is a proof, and so we would expect that it's got some theoretical elements to it. I'm wondering if anybody can, maybe you can use the chat if you want. Give me an idea what you're thinking. Like what tool or what is this about? Like what's this going to have anything to do with? Okay, so I've got an idea in the chat from Ben, which is to use Wilson's theorem. You know, the minute you see these factorials showing up, especially when the factorial that you have here, like 29 factorial, is very close to this 31 over here, it really makes me think that we're going to use Wilson's theorem. So actually, just to remind you what Wilson's theorem says, for Wilson's theorem, just so we have it on the board here, it just says that p minus 1 factorial is congruent to -1 in mod p. So p minus 1 factorial is congruent to -1 in mod p. What I like to do is, you know, instead of jumping straight to what we're trying to prove here with this expression, let's just write down how Wilson's theorem looks on paper first, and then we'll see if there's a way to kind of get it to become useful for what we're looking at, right? So for our solution now over here, you can tell already that the prime that you're going to be working with, the modulus, is going to be the 31, right? So 31 is the p. So by Wilson's theorem, what do we know? We know that, well, 30 factorial is congruent to -1 mod 31. Okay, so we can start with that. Just put that down. And again, guys, maybe you don't know how to do this problem, and on the test, you just can't put it all together. But if you write down Wilson's theorem on your paper, and even better, if you write down this first congruence, let's say you just write this much down and you stop. I'm going to be already able to give you some partial credit, and it might be fairly substantial for knowing which tool to use to do the problem. Even if you don't fully solve the problem, you want to go for every possible point that you can get on the test. So this is a good thing to write down instead of looking at the question saying, gee, I don't know how to do that, so I guess I'll move on, right? You're not going to get any points for that, but you can get points for this. So it's just kind of test taking strategy a little bit. I don't know how your other professors are, but I'm very inclined towards like incremental progress and giving credit for each sort of step along the way, even if you don't quite get the whole way to the end. So to take advantage of that. All right, so with that as kind of a first step, the issue here, though, that I see is that we don't want to work with 30 factorial. We want to work with 29 factorial. Does anybody have an idea how we could get this factorial lined up better to what we want?
30 times 29 factorial.
Exactly. I would start by just taking 30 factorial and doing something very easy, which is to pull out the 30, and that leaves me with 29 factorial. Still congruent to -1, and this is still in mod 31. Okay. And is there anything that we can do with the 30 that's right here? If it's in mod 31?
Change it to 1 or negative.
I'm sorry?
Change it to -1.
Exactly. 30 is the same as -1. I love it. Let's do that. So let's change the 30 to -1. So what we have is negative 29 factorial is congruent to -1 in mod 31. Okay, great. And actually, at this point, we can just get rid of the minus signs. We can let's put it this way. We can multiply the congruence through by -1. Okay, you can always take a congruence and multiply it through by any constant that you want. So let's just get rid of the minus because I don't even really want that. And so 29 factorial is actually congruent to 1 in mod 31. Okay, this looks good so far. And now, I'm to a point now where I've got my 29 factorial, which is part of what I'm trying to look at in the proof here. So I'm going to suggest now that we've done a little preliminary work to kind of use Wilson's theorem and see if we can somehow make it look like some part of what we're proving. Now I think we should really go after what we're trying to prove and see what we can do. Let's take a look at the number that we're looking at the top here. So then if we look at 4 times 29 factorial plus 5 factorial, I really want to continue looking at mod 31, don't I? 0 in mod 31. Divisible by 31 means congruent to 0 in mod 31. You starting to see where we're going to get the answer from? Right? The 29 factorial is just really 1. So I've really got 4 times 1 plus 5 factorial. And if you just work that out, 5 factorial is 120. Add 4 to that, you get 124. And mod 31, that is in fact going to reduce to 0 because 31 does divide 124. So there you go. It actually does work out to be a nice little application of Wilson's theorem. It's nothing too crazy about it. Okay. Any questions on that?
This is like, so Wilson says that p minus 1 factorial is congruent to -1 mod p, but
Yes.
it's also saying p minus 2 factorial is congruent to 1 mod p.
This is what I like, is when people take a look at Wilson's theorem and they say, gee, could we get more mileage out of that? Yeah, if you take the p minus 1 factorial and you just write it as p minus 1 times p minus 2 factorial, right? Then this p minus 1 is the same as -1, and you can cancel it with the -1 over there. And you're absolutely right. We end up with sort of a new, we could call this a corollary of Wilson's theorem, which is that p minus 2 factorial is congruent to 1 in mod p. So we'd never really made that note during class, but now we're seeing that, oh yeah, that seems to be like it's always going to be true here. So yeah, good observation, Tuan. Very nice. Okay, let's do another one. Just taking a look. I'm obviously going to save some of these for tomorrow's review. Let me do you want me to do an easy one or a hard? Well, I don't know how, that's a good question to ask. Let's do a slightly harder one, and I'm going to save an easier one for tomorrow because I think I want to, as long as I've got a big crowd here today, which is great. Thank you guys all for coming, by the way. I really appreciate this. Let's try one more problem tonight. It's also theoretical. We're going to try to do it, and then I'm going to save some more problems for the second review, okay? So here we go. I'm going to write it on the board right up here. Because at some point I need to take an hour break before I actually do my office hours. So this will be good to take a break after this one. So this is number 7. I'm going to just let capital S be the set consisting of 0, 1, 2, dot, 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 up to p minus 1. And this is going to be where p is prime. Okay, so p is some prime, don't know what. I'm going to define a function f that goes from s to s. So we're going to actually make a function right now via f of x equals x to the p minus 2 power. Okay? So we're making a function, and actually what I should really do here, let me write this a little bit nicer. Sorry, so I'm going to write this a little nicer, guys, sorry. F of x equals x to the p minus 2, and this is going to be in mod p. So once I calculate x to the p minus 2, I'm going to reduce it mod p. That's why you know that the result is in s. Does everybody understand this? We're plugging in a number between 0 and p minus 1. We're going to raise it to the p minus 2 power. And after we calculate that, we're going to reduce it back down mod p so that it once again is a number between 0 and p minus 1. So in other words, this is a function from s to s. What I would like to have us do for this last example, guys, is prove that f is 1 to 1. Ooh, that sounds different. Let's prove that f is 1 to 1. Okay, so I'm going to try that right here. So show f is 1 to 1. So this is where our Math 280 recollection about functions comes in a little bit. I know we haven't done a lot of problems like this, but I don't mind showing it to you now in this review, okay? 1 to 1 really just means, if you remember, that what it means is that if f of a is equal to f of b, then a is equal to b. That's what 1 to 1 means, that you learn in Math 280, and which you use a lot in actually a lot of different classes. Okay. So let's try and do this. The first thing I'm going to point out is obviously f of 0 is just 0. And f of anything that's not 0 is not 0. So 0 gets mapped to 0 by this function. So let's just write that down first. Let's just note that f of 0 is 0. So that part is not so interesting. So I'm going to consider a and b both not 0. Take the two numbers a and b, both not 0, and let's assume that f of a is equal to f of b. That is a to the p minus 2 is congruent to b to the p minus 2. This is all in mod p. So we're reducing everything mod p in this problem. So when we apply the function to a or to b, we're just taking the p minus 2 power of those two numbers a and b. Okay. Starting from this, I would like to prove that a is equal to b. Does anyone have any ideas?
Can we start multiplying both sides, I guess, by a and also by b, so we can get a to like the p or b to the p.
I like the way you're thinking, Tuan. This is a great suggestion. Look what mod we're in. It's a prime, right? And we're talking about powers. That makes me think of Fermat's little theorem. We should be thinking of Fermat's little theorem. Now, what Fermat's little theorem says is that a to the p minus 1 is congruent to 1 mod p, and b to the p minus 1 is congruent to 1 mod p. So if I really want to use Fermat's little theorem, I've got to get my exponents correct. They should not be p minus 2. So this was Tuan's idea, is to multiply through by, appropriate a's and b's to jack up the powers to p minus 1. And Brian has it in the chat really in the most, succinct way we could do it, which is to simply multiply through by AB. You guys are all over. I thought this was going to be a hard problem, but this is the idea. We're going to multiply through by AB. So let's write it down. Multiply through by AB. So on the left side, we will have A to the p minus 1 times b. And on the right side, we will have A times b to the p minus 1. This is, of course, in mod p. In mod p. And now, because A is not 0 and B is not 0, we can immediately just use Fermat's little theorem to finish the problem. So by Fermat's little theorem, right? B is congruent to A mod P, which actually just means, that A equals B, because the A and the B, remember, A and B have to live in S. So if two numbers are congruent in mod P, and they're between 0 and p minus 1, well, then they definitely have to actually be equal to each other. So this is kind of the idea. Yeah, I see some nice comments in the chat. This is a one-to-one homomorphism, and actually it's an isomorphism, because for those of you who know what that is, you have to have a one-to-one onto function that respects the operation, in this case, that operation being multiplication. There is one little problem, though, for those of you who want to know about this, which is that this is not a group, S is not a group under multiplication, because 0 does not have a multiplicative inverse. So we're not quite doing group theory here. If we wanted to make S into a group, we could, but we would have to make it into a group under addition. And I'm not using my function is not an additive function. So just ignore everything I just said. I'm just talking about Math 407 type stuff for a second. But that's the idea. It does feel a little bit like group theory, but it's not actually, doesn't quite qualify in that sense. Okay, so does this make sense? Are there any questions on the solution to this one? All right, well, guys, I really appreciate it. I have more problems, but I'm going to save them for tomorrow's review, because I need to take a break, but otherwise I'm going to be like collapsed for my office hours tonight. And I just want to give myself a little breather. And I think this is maybe enough for all of us to sort of soak up for right now. We've done 7 problems. We've done a mix of some calculation problems along with some theoretical problems. Tomorrow, I'm going to do more of the same, some more theoretical problems and also some more computational problems, just to practice. It'll be different problems than what we saw tonight. But as usual, if you don't want to come tomorrow, you don't have to. This is just totally optional stuff to practice and get ready for our test on Monday. So any final comments before we go today, guys? All right. Well, thanks for coming. Have a great rest of your evening, and I'll be talking to all of you again real soon, I'm sure. Good night, everybody.
Thank you.
You're welcome, folks. You bet.